This is a recorded webinar called Mist Collection System Design for Wet Machining, which is one in a series of educational webinars produced by Donaldson for engineers. It takes years of education and experience to become an expert in system design. The goal of the webinar you're about to watch was to provide an overview of the basics for wet machining.
All right, so Ashley Zook is going to kick things off for us today. Okay, good, we can see you, Ashley. And she's a channel manager here at Donaldson Company. She works closely with organizations across the United States, and one way that she helps them is through education, hosting webinars like this one, as well as in-person lunch and learns. And go ahead, take it away, Ashley.
Thank you, Amy. Thank you for everyone that's joined today. We're going to be starting off by reviewing wet machining processes and hazards. And then next we will talk about some common types of mist collectors. And then we'll get into mist collection system design, including sizing methods, mist collection strategies, and the four primary system components of hoods, ducts, collectors, and fans. And then we will finish up with a Q&A session. Please submit all your questions as you think of them in the chat box. Our experts, John and Brian, will address them towards the end of the session. In case anyone here isn't familiar with Donaldson Company, we've been solving complex customer filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the first filter for tractor engine. Today, we are one of the largest providers of unique filtration technology, and we excel at producing high-quality filters and parts. I am pleased to introduce our featured speakers today, John Danio and Brian Yapple. Brian is a territory manager for Donaldson Company out of Cleveland, Ohio, covering most of Ohio in a wide mix of industries, including automotive, grain, chemical, plastics, cement, wood, fabricated metals, and EV battery. Brian has been with Donaldson as a territory manager since 2002, and he has a bachelor's degree from Kent State.
Thank you, Ashley. I'm happy to be here today, and I'm looking forward to talking with you and everyone on this line about system design for mist collection systems. It's something that I do quite a bit and have been doing over a long period of time. So thank you very much.
And John is an industry segment leader for Donaldson. He has been helping manufacturers specify and improve their industrial filtration processes throughout the United States. He is experienced in implementing solutions for plants and metals and composite applications. He is currently focusing his effort in wet machining market and is improving efficiency results in metal working fluid mist control. John holds his bachelor's degree from Massachusetts State College and an MBA from American International College.
Thank you, Ashley. And yes, I do spend a lot of my time working in machining with machining process owners. And like Brian, I'm looking forward to talking with everybody today. As shared, our purpose today is to review the hazards, the technologies, and designs associated with mist collection. The bulk of our presentation will focus on metalworking applications because that's the most common. That said, we know there's applications like rubber and plastic machining that can also create mist, but generally the principles are the same. Mist collection for machining is a very complicated and constantly changing scope. We all know that machining is a subtractive process used to remove or chip away metal to create parts for other machines, tools, the transportation industry, and more. Wet machining brings oil or cutting fluid into the process for chip clearing, lubrication, and cooling. That's what you're seeing in the video here. Wet machining represents about 80% of the total market. The most common wet machining applications include milling, hobbing, turning, broaching, electrical discharge machining, cold heading, polishing, and parts washing. We're curious what the most common machining applications are for everyone on the call here today. So we're going to post a poll here, and please take a quick moment to respond and know that you can select more than one.
All right, looks like we have a lot in milling here. Also quite a bit in grinding, but it looks like we have a wide range of a lot of milling and grinding.
Okay. That's great. That's great for us to know, and both things that we'll be covering extensively today. Metalworking fluids are critical productivity enablers for all kinds of different machining applications. The most common types are water-soluble oils, synthetic and semi-synthetic oils, and straight oil. These metalworking fluids are usually complex mixtures of oils, emulsifiers, corrosion inhibitors, buffers, biocides, and other additives. Metalworking fluid mist and smoke is generated from the mechanical friction and heat of the turning metals in the high-pressure fluid delivery systems during the machining process. That mist then becomes airborne. It's critical to control the mist and smoke for multiple reasons, including productivity, stopping mist from settling all throughout the shop and on other equipment, or causing excess humidity that affects operations. Shop safety, like avoiding slick floors, Regulations, mostly meeting federal regulations, and of course, worker exposure. Also, another concern with the water-based metalworking fluids is the growth of bacteria and fungi. Now, the added biocides can help reduce microbial growth, but they have their own hazardous properties. If you're curious to know a little bit more about these chemicals, a good place to start is your SDS sheets. To better understand the properties of metalworking fluid mist, we need to know a little bit more about their particle sizes. As you can see from the chart, mist is very small in size. It ranges from 0.2 to 10 microns. It would need to be viewed through an optical or scanning electron microscope, and it's not visible to the naked eye. Mist particles under 5 microns will become an aerosol and will remain airborne indefinitely. According to associations like the Canadian Centre for Occupational Health and Safety, particles that are under 0.5 microns and smaller will make it into the lungs. They're classified as fine particulate matter that the EPA says could even make it into your bloodstream. So what are the health risks? OSHA states that over 1.2 million workers in the U.S. alone are potentially exposed to metalworking fluids and mist every day. And the metalworking fluids cause a variety of adverse health effects, including skin irritation, dermatitis, irritation of the eyes, nose, throat, bronchitis, asthma, which is one of the most common worker comp claims. And it's also known that exposure can cause certain types of cancers. According to OSHA's general duty clause, it's the employer's responsibility to identify and abate these hazards in the workplace. They put some regulations in place. Currently, OSHA's personal exposure limit for metalworking fluid mist is 5 milligrams in a cubic meter space over an 8-hour weighted average. NIOSH recommended limit is actually 0.5. This is measured in mass parts per million. To correlate, just 1 drop of water is about 50 milligrams. Some U.S. unions even have this written into their contracts. In other countries around the world, like France and Sweden, the limit is 1 milligram. Switzerland's exposure is 0.2 milligrams. The actual monitoring test for exposure is usually led by an industrial hygienist having a worker wear air monitoring device. But you shouldn't always rely on these sampling devices alone because the environment can change job by job, and so can the collector efficiency levels. In fact, the UK used to have a 1 milligram exposure limit, and they dropped it because they found it did little to protect workers and provided a false sense of security. So they changed it to ALARP, meaning as low as reasonably practicable. Now, before everyone starts panicking, you need to know that these goals can be achieved with a well-designed and maintained system. OSHA actually has a mist control best practices manual on their website that you can access, and the fact that you're all here today means you care about getting it done right. I want to touch quickly on some trends because most of the research and regulations that we've talked about already today are based on studies from the 90s, and we all know that machining technology has changed a lot since then. We see things like 3D additive machines and even additive wet hybrid machines come into the marketplace that need fume and mist collection. The drive for quicker production and more precise machining means faster tool speeds, sometimes increasing in the thousands of RPMs, and higher pressure deliveries of the fluids. This will obviously create more and smaller mist particles that are under that micron size. Now, the machine manufacturers have recognized this, and they've done well to try to enclose the machines as much as they can. The biggest trend we see is the overall desire for more effective and efficient mist control to minimize worker exposure. We actually did a mist market survey and found that worker exposure was the #1 concern, and many felt their system really wasn't optimized enough for their specific operations. OSHA identifies in this hierarchy of hazard controls that if you can't eliminate or substitute out the hazard, you need to turn to engineering controls as a primary control measure. Installing a suitably specified local exhaust ventilation system like a mist collector is exactly that. So before Brian gets into system design, we wanted to review a few mist collection technologies so you can understand the differences and choose what's right for you. The most common local exhaust ventilation system for mist uses multiple stages of cartridge or panel filters and gravitational draining. Here's how it works. The mist is pulled into the collector and moves through a series of filters, typically a pre-filter to separate out the larger particles, a primary filter to do the heavy lifting, and an after filter if needed. The smaller mist particles coalesce together as they hit the filters, form larger droplets that drain out with gravity. The best performing mist collectors have filters that are designed for the modern machining and are cartridge collectors. These are a combination of polyester and glass fibers for the primary filtration stage. As shown in the image, the polyester fibers are larger and drain well, whereas the glass fibers are smaller and provide higher efficiency. The fiber combinations vary overall, but these have proven to deliver high collection efficiency, sometimes in the high 90s in many processes. They also provide much longer filter life, often in the thousands of hours depending upon the application. On the negative side, they're not great for sticky or swarfy type mist that can plug up the filters. For those sticky and dirty mists, there are higher loft medias out there that don't have the tight-knit fibers that will work better, but they're not considered high efficiency. Here's a quick example of our high efficiency cartridge collector, the WSO. It's a 3-stage collector. It's very versatile because you can select your different stages for your specific process and efficiency goals. For things like water soluble, smoke, oil mist, you can get over 99% efficient down to 2 microns or smaller in some cases with just the primary filter. This primary filter is a little bit unique because it doesn't use resins to bind the fibers together, so it drains and breathes better. If you're generating a lot of submicron mist, you can always spec it with a HEPA. Another example of a multi-stage draining is a V-bag style collector. This is an example of a high loft media being used in an envelope style for the primary filtration. It can handle dust and grit and sticky mist that don't drain well. They're also modular, so you can spec and size it to your needs. The downside is they're lower in efficiency on smaller mist particles, and they don't last quite as long. There's also electrostatic collectors. These units work by ionizing the mist particles. Negatively charged particles are drawn to a positively grounded plate and drained. Electrostatic collectors were considered attractive because they don't have primary filters to replace, and they are considered pretty efficient when they're clean. The downside is the cleaning process can be a real maintenance hassle and is pretty frequent. This is likely why we've seen more OEMs and shops choosing other technologies. Lastly, centrifugal is the oldest technology out there that uses centrifugal force. It pulls mist-laden air into a drum with a rotating blade. The blade acts as a fan that pushes the mist droplets to an outside filter to coalesce and drain. They're usually okay for higher volumes of larger particles, but not nearly as efficient with swarf or smaller mist particles.
Thank you, John. I just wanted to remind everyone to make sure you submit your questions as you think of them in the chat box. John and Brian will address them at the end of the session. I see that we already have a question in there as well. Brian, can you get into system design?
Yes, thank you, Ashley. So first, I wanted to start off with a few videos of some installations so that you can see the importance of proper mist design. In this particular video, we have an electrostatic precipitator, and hopefully you can see there's a lot of mist and smoke that's bypassing the filtration system. There's several reasons why this might be happening. Most likely it's due to poor maintenance. As you remember from John's previous slide, electrostatic precipitators use plates, and when those plates get dirty, the mist and smoke is going to bypass. There's some other things that can possibly be going wrong in this situation. You might be using the wrong filtration technology, again, causing the plates to plug up quickly, or possibly the system's undersized. As you can see, you have this small mist collector going to multiple machines. The next slide is a chip removal system. And on the chip removal system, the mist is escaping out of the open area of the chip removal system. I wanted to just in the chat, if you guys don't mind, commenting on why you think mist and smoke is coming out of the chip conveyor. Yeah, we see a lot of good answers coming in. So there's actually several reasons why this could be happening. But in this particular situation, the system that was being used was a bit undersized, and they had a HEPA that was plugged. So combination of an undersized system plus a plugged HEPA, and then you have to evaluate why that HEPA was plugged. Was it because of the type of technology that was being used prior to the HEPA? So those are all factors that can come into play as to why mist might be escaping through the chip conveyor. Now, this next slide is an example of a properly sized system. There's no mist escaping. Yeah, you're using the proper technology because you can see at the end here that there's no mist bypassing the filtration system itself. Now, the only critique I would say about this installation is that they're using spiral duct, which is a no-no in mist collection applications. But we'll discuss that later in the presentation. So a lot of times you'll be buying a new milling machine or a CNC, and I saw a question about this earlier, and it already comes with a mist collector mounted to the system. And then when you fire this system up, you realize that the mist collector supplied is not adequate for your application. This is usually because the machine manufacturer or distributor may have undersized the application or the wrong technology was selected for the application. This is pretty common with OEMs because their expertise, quite frankly, is in selling that CNC in that mill. and not necessarily the mist collection system, even though it's a vital component to the entire system. So it's important to understand how to size a proper mist collection system for your application. Now, there are several methods that we use for sizing mist collection systems, and I wanted to review these with you to help better understand when to apply the appropriate method. Now, we're going to talk about three methods: the air exchange method for enclosed machines, the open door method, and then the fan speed method. The air exchange method for enclosed machines is a commonly used calculation for sizing mist collection systems. This calculation requires that you take the total enclosure volume where mist is being generated, and you multiply that value by the desired number of air exchanges per minute you would like to have in the enclosure. So in most cases, we're going to look at 3 to 4 air exchanges a minute because we really just want to keep the mist contained to the enclosure. Now, when using this method, you also need to take into account any constant openings, such as a chip conveyor, as we saw on the previous slide, which has a discharge chute that is always open. When calculating your constant openings, you need to take the area in square foot of that opening and multiply it by a recommended in-draft velocity of 125 feet per minute to get the airflow requirement for that specific opening. So let's walk through an example of a CNC lathe and how we would calculate using this method.
The first step is to calculate the internal volume of the CNC lathe where mist is being generated. For simplicity's sake, let's say that we have a 5 foot by 5 foot by 4 foot enclosure, so we get a total volume of 100 cubic feet.
Next, I'm going to multiply that 100 cubic foot volume by the desired airflow exchange rate based on the chart shown here in the slide. In most cases, our goal is simply to keep the mist contained to the enclosure. So we were going to look at 4 air exchanges a minute in this particular case. So 4 times 100 cubic foot, we need 400 CFM to keep the mist contained in that enclosure. We now need to evaluate all the constant openings. So as you can see in this picture, the lathe is pretty well enclosed, and the only constant opening is the discharge chute on the chip conveyor. So we want to, let's say the size of the discharge chute is 1 square foot. So we want to multiply that area by a recommended in-draft velocity of 125 feet per minute, and we're going to get 125 CFM that's required for that chute. So you add the 125 CFM to the 400 CFM for the enclosure, and we have a total airflow requirement of 525 CFM for this particular application. Now, sometimes the enclosure method may not be practical for the application, and it may be better to use the open door method instead. This method examines your door opening sizes and all constant openings to determine your airflow. So to calculate, we will first examine your door opening and determine the type of door you have. As you can see, we have 3 different types of door openings with recommended in-draft velocities based on the door type. You will take the recommended velocity and multiply it by the area of the door opening. This value will generate enough airflow to keep the mist contained to the machine when the door is open. So next, we're going to evaluate our constant openings like we did in the air exchange method, and we're going to take that area of those openings and we're going to multiply it by 125 feet per minute. Now you're going to add both of those values together, and that'll give you your total airflow requirement using this method. So let's look at an example of how to calculate this method. So let's say we have a machine center that has a door opening of 10 square foot, and the door type for this machine center is a type 2 door. The enclosure is very good, and the only constant opening we have is that chip conveyor that has a 1 square foot opening at the discharge. So I'm going to take the area of that door opening, which is 10 square foot. I'm going to multiply it by the recommended intake velocity of 50 feet per minute for a type 2 door, and this will give me the value of 500 CFM. I will then take the 500 CFM, and I'm going to add my constant airflow openings to the value. In this case, I have a total opening area of 1 square foot through the chip conveyor. Like the enclosure method, we need to multiply that by 125 CFM. So for this example, we're going to need 500 CFM to contain the mist at the door, and we're going to need 125 CFM to handle the constant openings for a total airflow requirement of 625 CFM.
Hey, Brian, when would you use this over an enclosed method?
That's a great question, John. Typically, the answer is it depends. But in most cases, you're going to use this method if you have really fast cycle times and you're opening those doors immediately to try to change out the parts. This is when you're most likely going to use this method over the enclosure method, just so that you can protect your employees from getting blasted by mist when they open that door. So the next method is the fan speed method. Now, this is typically used in applications where you do not have an enclosure. You need to strategically place a hood to capture that mist. So a common example is wet grinding applications, which I saw a lot of people that have wet grinding applications in your facilities. So using this chart, you're going to take the diameter of the wheel and you're going to compare it to the speed of the wheel to get the recommended airflow. If the RPM you require is not on this chart, you can find the calculations in the industrial ventilation manual, which we'll talk about a little bit later. But typically, most wet machining applications that are enclosureless are not going to operate at speeds higher than 3,500 RPM. Now, if you do have that case where you are operating over 3,500 RPMs and you don't have an enclosure, I would strongly recommend that you enclose the machine for best performance and overall safety. So, after determining the airflow requirements, we have a few more considerations to review in order to choose the proper filtration technology. We need to know the type of coolant. Is it a water-soluble, semi-synthetic, or straight oil? This is going to help us determine the proper filter for your system. What is the spindle speed and coolant pressure? When you're dealing with higher spindle speeds and coolant pressures, they create a finer mist that's a lot harder to filter, especially with some of the older technologies that are available on the market. So when you're dealing with spindle speeds that are over 10,000 RPM and you have coolant pressures that are above 80 PSI, you may want to consider one of those high-efficiency cartridge systems for those types of applications for some of the older technologies. We want to know what the cycle time is. How quickly are you changing these parts out? As you saw from a couple slides earlier, that can help us determine the proper airflow sizing techniques that we're going to use. We want to know the operational use. Are you running 24/7? A lot of these applications may require, long times where we need some drainage. This can impact the sizing of the mist collection system. So in order for us to ensure you have the best filter life or the best technology, we need to know how often you're running this and if there is any downtime available. So any of these questions, you're going to provide those answers to your mist collection manufacturer so they can hopefully provide you with the best filtration technology for your specific application. So one of the cool parts of my job is just how unique every project is, from how the part is being manufactured or the type of materials being used, the processes and types of machines all vary, and that brings different variables and challenges to each job. That is why there is not one solution that fits all or one collector that fits all. So when we're evaluating mist collection for your facility, you need to consider the plant layout and how that impacts your usage of mist collectors around your facility. Placement of your mist collectors can impact floor, head space, as well as process flow. So when determining how to implement mist collection in your facility, there are generally 3 strategies to consider when determining placement of your systems. We have 3 approaches. We can do the singular machine collection, where we have one mist collector for one machine. We have the cellular approach, where we're going to group a series of machines to a collector based on a product line or a part that's being manufactured. And then we can look at the centralized collection approach, which is a whole plant approach using a single machine. There's pros and cons to each one of these strategies, and you need to understand them when you're determining the arrangement of the systems. So the first strategy involves a single machine connected to a dedicated mist collector. This approach is most commonly used strategy because it allows flexibility in how the mist collector can be mounted. The mist collector can be mounted directly to the machining center, eliminating the need for ductwork, or in close proximity to the machining center using a short amount of ductwork. Some of the other advantages, you can match the application with the correct technology for the job. You have the ability to move the equipment as the process changes. That's a huge point right there for this strategy. You only use the mist collector when the machine is in use. It's easier to reclaim the coolant because you can drain it right back to the machine center's coolant reservoir. Maintenance can be done a lot easier because, again, you're only maintaining that machine and you're not worrying about having to shut down an entire process like a central system. But there's some disadvantages. You could be paying a higher price for multiple individual mist collectors versus buying one system to handle multiple machines. You could potentially have more filters to maintain and dispose of over a central or cellular system. The cellular mist collection strategy typically consists of 3 to 5 machine centers being served by a single mist collector. Often this machine performs sequential work on the same part, and all machines typically will use the same coolant system. So some of the advantages of this approach is maintenance can be easily done during downtime of the manufacturing cellular line. Another advantage is you will have lower capital equipment costs because you're buying one mist collector to handle multiple machines. Your energy consumption can be lower because, again, one collector versus many collectors. But there's disadvantages. Number one, there's no flexibility if your process changes or if the equipment needs to move. You're using ductwork, and ductwork can leak, causing slip hazards around your facility. And if your ductwork isn't designed properly, you risk insufficient airflow to that particular machine or the potential for materials settling out in your ductwork. And then finally, with larger air volumes, you may require to get an air permit for the process, even if it's located indoors. You're going to want to consult with your local authority having jurisdiction on permitting requirements in this particular case. So the final strategy would be a centralized system for all machines. Now, this was a real popular approach about 15 to 20 years ago, but it's not too common today. The solution has a lot of the same pros and cons as a cellular system. However, the disadvantages typically outweigh the advantages. If the mist collector is down, the whole plant is down. It's more difficult to reclaim your coolant. Installation costs could be greater depending on the amount of ductwork that's required, and you have more potential leak points throughout the plant. There's no forgiveness for that challenging oddball application that may get mixed into the process, and there's no flexibility for changes in the process or if you need to move equipment around. So when you're using a cellular or a central approach, I recommend that you work with a qualified filtration expert to provide the right system and duct design for your application. So we've given you the basics in sizing mist collectors and strategies in implementing mist filtration in your plant, but you still need to understand the components of a well-designed filtration system. And there's 4 main components to mist filtration. The first component is the hood, and that's used to capture the mist. The next is the ductwork to convey that mist to the filtration device. The third is the filtration device to clean the air. And then finally, you have the fan, which moves the air throughout the entire system. If you incorrectly design any of these components, your system may not perform to expectations. So it's important to understand what goes into designing an industrial ventilation system. Now, I use that word industrial ventilation because this is totally different from an HVAC system. HVAC systems move clean air, and we are moving material, which is a whole different animal. So when designing an industrial ventilation system, we have 2 main objectives. First, we want to accurately predict the air volume in CFM that is required to effectively capture and control that mist at the point of generation. And then secondly, we want to minimize the total energy required in horsepower to produce those airflows. So the publication shown here is the Industrial Ventilation Manual, which is published by the American Conference of Governmental Industrial Hygienists. The Vent Manual offers guidelines to proper ventilation design, and it's considered by many, including OSHA, the standard for ventilation design. So if you have any interest in developing your design skills further from what you're learning today, you may want to consider purchasing this manual or attending the various classes that they offer throughout the year. So let's get back to system design. So the first component of the system is the hood. This is a starting point for designing a filtration system, as this is where the airflow is determined for the process. Now, a well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the mist where it is released, while minimizing the amount of energy required to do this. So some of the common failures I see on the job on a daily basis is either someone's using the wrong style hood, maybe the hood's not located in an effective location, so it's either too far away or maybe too close, or you have inadequate airflow at the hood. In most mist applications, though, we're fortunate because the machine enclosure will be the hood. However, there are those times when the hood is required, such as a wet surface grinding application. And I know by looking at the poll earlier, there's a lot of people on here that have wet grinding applications. So we typically want to design that hood so that we can get as close as possible to the application without interfering with the process. And we want to provide just enough airflow to capture that mist into the hood. Now, when determining the required airflow at the hood, the main design factor is called the capture velocity. This is the velocity required to capture the mist into the hood, with the main goal being to keep the operator safe and keep the particulate away from the breathing zone. Capture velocity recommendations vary based on the application and typically ranges from anywhere from 150 to 500 feet per minute. The importance of capture velocity comes into play with applications where you do not have an enclosure to contain the mist, and you're using a well-placed hood to capture that contaminant. But typically, if you have a rotating part like a grinding wheel, you're going to want to use a higher capture velocity to overcome the effects of the rotating part. If you're not sure about the best capture velocity for your application, I would recommend that you consult with your local filtration expert, or you can refer to the Industrial Ventilation Manual for recommendations and guidelines for your particular situation. So once you've determined your capture velocity requirement and you've determined the best hood design for your project, we now need to calculate the CFM. So to determine the CFM or airflow, you will take your capture velocity and you're going to multiply it by the area of the hood opening. And this is going to give you the airflow or CFM for your process. So once you determine your airflow at the hood or the enclosure, the next step is to convey that mist to the filtration device. So a properly designed duct system should pull the minimum airflow required at each hood while maintaining enough conveying velocity in the ductwork to transport that contaminant to the filtration device without any material settling out in the ductwork. Now, you should do this using the least amount of energy as possible so that you minimize any wear and tear in your duct components and you reduce the amount of fan or horsepower required to move that air through the system. Some of the most common mistakes I see in duct design is either the wrong type of duct being used, especially in mist collection applications, the wrong diameter ducts being used, or the system wasn't balanced and you have improper airflow at the particular machines. So a critical design factor in sizing your ductwork is evaluating your minimum conveying velocities, which is the lowest velocity where all contaminants stay suspended through the duct system. If you go below this velocity, mist and contaminants could settle out within the duct and cause other safety issues. Now, the Industrial Ventilation Manual recommends 2,000 to 3,000 feet per minute for wet machining applications. However, from experience, you're always going to capture chips and other solids in the airstream, and those are heavier. So you're typically going to want to recommend sizing your ductwork so that you convey between 3,500 to 4,500 feet per minute.
Ryan, quick question. What if we size our velocity at higher than recommended speeds? Wouldn't that ensure no material ever gets settled out in the ductwork?
Yeah, absolutely, John. I mean, you could take that approach and you may not have any issues with material settling out in your ductwork. But when you go beyond the recommended conveying velocities, you're going to require more energy to move that air through the system. And ultimately, this can impact the size and horsepower of the fan, as well as create issues such as increased noise in your ductwork, possible abrasion, and just more wear and tear with your ductwork. So you got to be careful not to go too high in your conveying velocities and create other problems. So let's just talk about the types of ductwork we want to use. So in mist collection applications, we want to use all welded flange ductwork typically, and we want to make sure that there's gasketing material that's resistant to oils in between those flanges. If you're using those clamped together type duct systems, most of those manufacturers do have gasketing material that's designed for oil mist. So you want to make sure that you incorporate that instead of using the standard clamps that they offer. You want to make sure all your elbows are caulked, otherwise you will leak at your elbows. We want to avoid at all costs using rectangular ductwork. Rectangular ductwork is great for HVAC systems because, again, we're moving air, but we are moving material, and you're more at risk, especially on the dirty side, of using rectangular duct where material might settle up or build up in the corners. We want to avoid spiral duct at all costs. Spiral duct in mist collection, in my opinion, is a no-no. It doesn't have a smooth interior, which creates more resistance in the system, which creates more system static pressure, which we'll talk about a little bit later. More system static pressure equals more fan. The duct also tends to leak air through the seams, which can impact the design airflow by almost 10%. And if it's leaking air, you can bet it's probably going to leak oil as well. So let's try to avoid using that. There's better ductwork that's available on the market that's reasonably priced. We want to look at, when we're looking at our drops and our branch entries, we want to avoid T's and we want to avoid short radius 90s if all possible, because those create a lot of resistance. We want to look at long radius elbows, or we want to look at 30 to 45 degree branch entries into your main duct lines. And then finally, we want to minimize the use of flex hose as much as possible. Now we know, flex hose may be needed for some of those more challenging connections, but we want to use as little as possible because there's a lot of resistance to flex hose. Like spiral duct, flex hose is actually worse because it has a lot of rigid points and creates a lot more resistance. And to kind of give you an example of that resistance, if you have 1 foot of flex hose that's straight, that's the equivalent of like 3 feet of straight duct. If you put a bend or 90-degree bend in that flex hose, that could be the equivalent of 40 feet of straight duct. So you just want to minimize that as much as possible so that you don't impact the overall performance of your fan and your system design. So the third component, we got good hooding. We've got the mist going to the collector. Now we're going to talk about the mist collector. So early in the presentation, we discussed the different types of filtration and how we go about sizing a system. So we're not going to get into any more deeper discussion on that topic. But from a filtration systems design standpoint, just remember the objective of a mist collector is to deliver sufficient cleaning efficiency while operating in a predictable, stable condition and in an economical fashion. Probably the most common mistake I see out there is the wrong filtration technologies being used for the application, or someone sizing the filtration too aggressively, so it's causing shorter filter life. Incorrect airflows are not being used, and we're going to talk a little about airflows in a minute here with fans. And then finally, just poor installations can sabotage a mist collection system in that design. So the last component, but the most critical, is the fan design. The fan is the heart and soul of the local exhaust ventilation system. It has 2 job responsibilities. First, a fan must deliver the necessary volumetric flow at the required static pressure to drive the operation of the system. And since pressures change in the mist collector as filters get dirty, we recommend that you size your system using dirty filters. So you want to size it so that you can achieve that airflow with dirty filters. Secondly, the fan you select should be able to deliver the desired airflow and static pressure using the least amount of energy at an acceptable sound level. Now, mist collectors are unique to most other types of collectors in that a lot of the fans are integrated into the collection system. These are typically designed for point of use or minimal duct runs. When you're using a cellular or central design approach, as we discussed earlier, you need to be careful when you're using integrated fans and evaluate the total system static pressure to make sure that the integrated fan can meet the requirements of the system. If it cannot, and in some cases it doesn't, you'll need to use a custom fan or a specially designed fan for that application. I've said the word static pressure quite a bit. It's a critical component in fan design. Basically what static pressure is, it's the overall resistance that the airflow must overcome due to system components like your hood, your ductwork, your filtration system, as well as evaluating the density of the air based on air street temperatures and elevations. And it's typically expressed in inches of water gauge. So before selecting a fan, you need to calculate your total system static pressure to determine the proper size fan for your application. So let's take a look at an example of a project where we may need a mist collector. So let's just say we have a project where we need 18,000 CFM. We have multiple machines that we're going to be connecting to. And I'm talking to my local torrent rep, and he feels that for my application, the WSO 25-2 is the appropriate unit for this application. And then the rep states that, this system does have an option for 7.5 horsepower integrated fan. And we need to evaluate that total system static pressure to see if that fan, which will save us some money, will work for our particular application. So we know the temperature is ambient. We know the elevation's below 500 feet. This is important to know because density of the air may be lighter or heavier depending on the location, which can impact your fan design. So depending on where you're located in the country, you need to make sure you convey your elevations and your temperature requirements to your reps when you're sizing a system. So let's look at the components of this particular example. So let's say we have, we're going to lose about 1 inch for the hood. Let's say we have 7 inches of loss through all of our ductwork and elbows. And then, as I mentioned earlier, we want to size for 6 inch. We want to size for dirty filters. So let's figure 6 inches of loss for the filtration device. So we have a total static pressure of 14 inches. So let's look on the next slide and see if the integrated fan that's an option would work for my particular process. So as I mentioned in this example, we need 1800 CFM and we calculated out 14 inches total of static pressure that's required. The mist collector we chose has that integrated fan package. So this is the curve that's shown here of the integrated fan package. Now, as you can see, this fan will produce 1800 CFM, but only at 8.75 inches of static pressure, which is well below what we need for our requirements. So we're going to have to look at a different type of fan package for this particular system using that WSL 25-2 technology. Now, I'm using this as an example because just because a system says it's rated for 1800 CFM doesn't actually mean it will produce 1800 CFM. You need to be careful of that because you see marketing brochures out there all the time that state that. You need to look at your total system design in determining if that fan package will meet your specific application. So now that you have, the 4 components of proper ventilation design, you should have a better understanding of what a good system looks like. We've given you guidelines on how to determine proper airflow sizing, and we've even talked about the different types of filtration technologies that are available on the market. And hopefully you have learned that the one-size-fits-all approach is not practical in today's machining processes. John's going to wrap up this presentation with a few options that are available that may be important for your particular project. John, fire away.
Yeah, thanks, Brian. And just a few final points here. We do frequently recommend after filters like HEPA filters, which are mats of randomly arranged fine fibers. We do this when a customer is looking for ultra-high efficiency in their recirculated air. They can deliver 99.97% efficiency down to 0.3 microns. Many shops want a HEPA on everything, which is great, but remember, you really need to look at your whole system and the primary filter is being optimized, or you're going to spend a small fortune replacing HEPAs. We often see shops with centrifugal collectors burning through HEPAs. Also know that when they plug up, it'll back up the entire system like a clogged sink, and mist will find a way out. Just a quick note, there are dispersed oil particulate after filters, which are 95% efficient down to 0.3 microns. These last much longer for heavier mist loading applications. You also need to look at drainage. A properly designed drain system is also critical. Drains allow the collected mist to empty out of the system while it's running. You have to keep air from flowing back up through the drain system. You do this by preloading a liquid barrier into the system between the collector and the ambient air. Typically a 1 or 2 inch loop drain hose is commonly used. Otherwise, you can use a metal P-trap that works like a sink drain. When there's only a little bit of fluid drained, you can empty it into a small container. The last thing we have to present today is on monitoring and controls. Every system should have a primary and sometimes a secondary static pressure monitoring system to gauge operating airflow. You typically want static pressure under 4 inches of water gauge for proper air movement. When it gets over 4, you'll likely need to replace your filters or run a maintenance check. Finally, a mist collector needs a motor starter to turn the fan on and off. So you need to think about who's going to do this. Consider connecting the controls to a machine tool interlock so it starts when the machine turns on. Otherwise, you can have the controls integrated into the junction box that's on the machine, or if it's a ceiling mount, for example, you can have a wired remote pendant that hangs down and you can mount it anywhere you want. There are other options like VFDs and delay timers that you can also spec. Designing a good mist collection system is a mystery that changes with every shop and process. Sometimes we just need a little help to figure it out. Please know that we have local resources like Brian in every market that can help you clear the air.
Thank you, John and Brian. And thanks to all that have participated in today's webinar. We're going to finish up with a Q&A. If you have any additional questions or if you want information scheduling an in-person lunch and learn at your company, John's contact information is on the screen. So here's our first question. Can I retrofit a HEPA onto a current mist collector?
Yes, you can put a HEPA onto a current mist collector, but you should also recognize it's going to affect your total airflow, right? So if you designed a collector for the airflow you need, as Brian went through the sizing exercise, and you put a HEPA on there, you may not keep that level of airflow you need for proper efficiency. So there's also the fact that you may have the wrong filtration technology for the primary filter, so you're going to plug up that HEPA and you're replacing a lot of HEPAs. So it can be done, but it's also challenging based upon what level of airflows you have and your primary filter technology.
All right, second question we have here. The first one was answered, so I'll go to the second one. Can a cyclone be used in any of these applications?
So I would say, I'll answer that, John. So sometimes, especially like in a wet salt cutting application where you're dealing with a heavy amount of chips, you may want to consider using a cyclone pre-filter to knock out those chips so that you're not plugging up your primary filter system. That would be the only time I would use a cyclone in those applications. So hopefully that answers your question.
Next one. Does Donaldson have a plan to update the WSO line with a modern look and controls?
Yeah, I can take that one, Brian. Yep, I'm working in the headquarters, and I can tell you that Donaldson's always looking at advancing our technologies. I can tell you that there are active projects looking at mist collection technologies, and we have a team looking at that. These things take time because we want to make sure we get things done, dialed in right, that we have the same range of flexibility that we have with the WSO, which has been on the market for 20 years and has performed very, very well. So the efficiency is there, but certainly, the goal is to have more modern looks and controls is always something we want to consider. So yes, we are looking at something as we speak.
Okay. For an enclosed area, are there any makeup air requirements when designing a system like this?
I'm sorry, can you repeat that, please?
Yep. For an enclosed area, are there any makeup air requirements when designing a system like this?
So here's the thing. With enclosures, most of them aren't sealed totally tight. So you're always going to have air that's going to come through the cracks of the doors. It's going to come through your chip conveyors. So you're not necessarily, you don't need makeup air for that. The answer to the question, Charlie, I don't know of any enclosures that are super tight. So.
Okay. Are there any considerations for explosion protection?
I know fire protection sometimes on some oil applications is definitely a consideration, but usually that is being done in the machine center itself. We may offer like a sprinkler head if that, but typically the machine enclosure will have the protection for fires. This is a wet application, so not necessarily you won't have explosion issues so to say, from dust, combustible dust application. So.
Yeah, I've seen it sometimes with EDM machining, Brian, where you may have to bring in some fire protection, but not explosion. I have not seen that anywhere, but certainly we have integrated in fire protection features into a mist collection in some applications.
All right. Next question. With quality machine enclosures, can mist collectors be run intermittently, turning on before the part is completed, creating the negative environment so that the operators do not get blasted when they open the door?
Yes, you can. I mean, here's the problem with that is, and this is where you have to work with your machine integrators, because, theoretically, when that door is closed, you shouldn't need as much air because there's only those cracks that we talked about earlier. And, you have your chip conveyors where mist, it could potentially escape. So you want to keep a negative opening on that. But the problem is coordinating the controls with your machine manufacturer. When is the operator going to be opening the door? When are they dialing back the part? You need to still have air moving at a certain speed and a certain turnover rate inside of that enclosure. Even if you decide to ramp it up right when the operator closes the door, that might be too late. So there is a means of doing it, but it's how do you coordinate with the OEM part of it, the piece of machine. John, you want to expand more?
Yeah, and I would say your machine tool interlock, you can, if you're connected right to the machine, you can have delay timers on there. So I imagine you could have a delay timer that turns the mist collector on right towards the end of a cycle. But we don't typically see that because you're generating mist during the machining process. Typically what we'll see is we'll have the mist collector running. At the end of the cycle, you let it run a little bit longer before you open the doors to clear out the mist that's inside the machine. And that can be done through connecting the machine through a machine tool interlock and having that delay timer in the controls.
All right. Next question we have here is what do you factor in for static drop in HEPA, clean and dirty?
Well, you always want to size for dirty filters. So, I mean, typically you want to figure about 2 inches for after filters.
Okay.
Yep, I think that's fair.
All right. And then last question so far on the question here is any recommendations for volume damper used knife or butterfly type?
So I'm assuming this question's referring to like ductwork systems to try to control the airflow from that standpoint. Is that what I'm gathering here?
Yeah, that's right.
I guess if I understand the question correctly, if this is for a remote mounted mist collection system and not mounted to the actual machine enclosure, using any kind of airflow device is difficult because you start risking your velocities inside your ductwork to drop below the minimum conveying velocity. So, kind of going back to the question that was asked before in regards to, hey, can I dial back the airflow when when the door's closed? And the answer is, if your mist collector isn't mounted to your machine center or your lathe and it's independent, there's ductwork that's involved, then the answer is no, because you have to maintain your conveying velocities. The only way that would probably work in adjusting your airflow is if it's mounted directly to the machine with no duct.
Yeah, Brian, we have seen a lot of people use slide gates on their ductwork to try to tap down if they've oversized their mist collector, say, to tap down. And we do see that being used pretty regularly. We also see them leak a lot, which creates a whole other problem. So the goal, I think, is to get that airflow as close as possible to the need, and try to avoid the slide gates because, again, if you're generating a lot of mist, they do tend to leak.
All right. It looks like we don't have any other questions. I do want to thank everyone that joined today. I know Amy just answered the question about the presentation. Like I said, you can contact John with his information that's on the screen. But I thank you for everyone that joined today, and I appreciate your time. And hopefully you guys learned some stuff from it today.
Yeah, thank you. Thank you, Ashley. Thank you, Brian. Thank you, everyone, for joining us today.